Okay, in this video, we are going to look at a concept or a mechanism of Turing reducibilities and Oracle Turing machines. Okay, so earlier we looked at reductions, and in particular, we defined mapping reductions or many-to-one reductions. And today we're going to look at Turing reductions, and then we define what it means by Oracle Turing machines. Okay, so first let's look at a limitation of many-one reductions. So intuitively, A sub Tm, so remember that A sub Tm is the set of outcodings m comma x, where m is a Turing machine and accepts x. So that's A sub Tm. And then the complement of A sub Tm will be the same same type of instance, but now this m does not accept x. So this A sub Tm complement is the same set of instance, but m doesn't accept x. Okay, so we know that A sub Tm is not decidable, and complement of A sub Tm is not even Turing recognizable. So intuitively, so these two languages should be reducible to one another, because an answer to the complement of A sub Tm can be reversed to become an answer to A sub Tm and vice versa. So why can they reduce to each other? However, using many-one reductions, we know that the complement of A sub Tm is not reducible to A sub Tm because A sub Tm is Turing recognizable, but the complement of A sub Tm is not. So if it is reducible, then the complement of A sub Tm should also be Turing recognizable, but we know that it is not. So that means the notion of mapping reductions will not satisfy our intuition. So what can we do with it? So because of this, they just flip, right? So A sub Tm accepts, and the complement of A sub Tm doesn't accept, so they just flip. So then it's easier to generalize this notion of mapping reduction to allow Turing machine computation. Okay, so then we are going to define Turing reductions. In order to define Turing reductions, we are going to, or we need to define Oracle Turing machines. And Oracle for a language B is an external device that is capable of reporting whether any string W is a member of B. Okay, so this Oracle is something like a more powerful thing, so he can give you an answer whether X is in B or not, without so you make a query, right? So let's say I have an Oracle for B. We are given an instance of B, X. I want to know whether X is a positive instance or a negative instance. By positive instance means that it is in B. By negative instance means that it is not in B. So now I have Oracle. I make a query, the Oracle will tell me whether X is in B or not. So that doesn't cost me. So my only cost is that query. So I make a query, I get an answer. All right, so an Oracle Turing machine then is a modified Turing machine that has the additional capability of querying an Oracle. So in that regard, we're going to write M to B to describe an Oracle Turing machine that has an Oracle for language B. So this Oracle is for language B. So at some point, let's say on input X, at certain point, I generate a Y. I want to know whether Y is in B. I can simply make a query to B. So that is the notion of Oracle Turing machine, and then we're going to use OTM to represent it. Okay, so then it is straightforward to decide the complement of ATM by an Oracle Turing machine with an Oracle A sub TM. So, so that means I have a Turing machine M with this Oracle, and I want to decide the complement of A sub Tm. So that means that on any input, so this M, so this Turing machine, so this itself is a Turing machine. And let's say on a Turing machine M and X as input, okay, I want to know whether it is in A sub Tm bar. Okay, so then I just make a query. So I made a query to A sub Tm. So if the answer is no, then this Oracle, this OTM accepts. If the answer is yes, and it rejects. So then with this A sub Tm as Oracle, this Turing machine, this Oracle Turing machine decides the complement of A sub Tm. So that's straightforward. So then let's look at the second bullet. So any language is decidable using itself as an oracle, because you can just make a, because you have a powerful oracle. So if I want to say, I want to know whether instance X belongs to this language, I just make a query to an oracle, then I immediately know the answer. So that's decidable with itself as an oracle. And then the emptiness check, okay, so whether the Turing machine accepts nothing, is decidable by an Oracle Turing machine using A sub Tm as an oracle. So here's a proof. So we construct this Oracle Turing machine T to the A sub Tm. So that means I'm using this as an oracle such that on any input or any instance, which is encoding of M. Now remember, we want to know whether this M accepts nothing. Okay, so then we construct the following Turing machine T sub M. So on any input X, now this is a machine, this is input. I construct a new Turing machine T sub M such that on any input X, it runs M in parallel on all strings in sigma star, which means that I list all the strings in lexicographical order, and I run M on these strings in parallel means that we run them concurrently. So let's say we run on X1 for one step, and then move on to run x1 and x2, each of these for 2 steps, and then if one of them, so that's simultaneously, right? If one of them halts, then it halts. Otherwise, you run x3 for 3 steps and so on. So that's what it means that it runs M in parallel on all strings in signal star. So it accepts X, okay, if one of the computation accepts. So know that it only generates the encoding T sub M. Now, when we say it constructs this Turing machine, that means that it only generates this description, okay, without actually running it. So this is the description of this TM. So that means that it generates the description. So now this Turing machine asks if T sub M, now it has a description comma 1, which is on input 1, is in ATM. Okay, just ask a simple question. So ATM is Oracle, it returns yes or no answer. So if the answer is no, so that means T sub M so it means that M okay, so it will make this query. So if the answer is no, then this Oracle Turing machine accepts the input, which is encoding of M, otherwise it rejects it. So with this Oracle, we know that this OTM on this input, so without this, on this input, which is the encoding of M, always holds. And if M doesn't accept anything, then this T sub M doesn't accept anything because it will, so when it runs M in parallel on all these strings, none of them will accept because M doesn't accept anything. So then that means TM won't accept anything. So that means that if L of M is empty, then L of T sub M is also empty. Otherwise, okay, if M accepts something, then one of these strings will be accepted. So then this computation will hold, okay, on any input X, okay, on any input X. So that means that L of T sub M is sigma star. So this should be T sub M. So then, so this means that if M doesn't accept anything, then T sub N doesn't accept anything. Hence, this query returns no. That means then T to the A sub Tm accepts input M. Otherwise, M accepts something, then T sub M accepts anything, that of course including accepting 1. So then the answer is yes. Okay, so the query, so this query to the Oracle, the answer is yes. And so T, so A sub Tm rejects this input M. Okay, so so that's how this Oracle Turing machines decides E sub Tm. All right, so now we defined Turing reduction. So a language A is Turing reducible to language B, written A less than or equal to sub TB if A is decidable by an Oracle Turing machine with B being an Oracle. In other words, A is decidable relative to B. Okay, and we have the following immediate result. If A is Turing reducible to B and B is decidable, then so is A. Okay, so the proof is straightforward. Since B is decidable, so that means for any query, it returns an answer. Okay, so that means that we can replace that B by a Turing machine decider, because a composition of two Turing machines is still a Turing machine. That means then A is decidable, right? So, so what it means here is that so B is decidable, so it has a decider D for B. Okay, so that for any input X, it returns a yes or no answer by a Turing machine DB. So then because A is reducible to B, so that means we have T using this. So this is a Turing machine. T is a Turing machine. DB is a Turing machine. So this really means it's the composition of these two Turing machines that is also a Turing machine. And this Turing machine, no matter what input you are given, always holds. Okay, so so that, so in other words, I want so let's say B is decidable, A is decidable. So I just want to say that given as X as input, as instance of A, I compute this Turing machine TB of X. Okay, and this TB is just really T of dB of X. Now this is a Turing machine always holds. Okay, so that means this Turing machine decides X, because if X is in A, this Turing machine returns yes. If X is not in A, this Turing machine returns no. So, but this Oracle Turing machine just this machines, right? So that's why A is decidable. Obviously, if A is many one reducible to B, then A is Turing reducible to B, but the reverse decision doesn't hold. Okay, so we already know the answer. Why this is the case? Because we have that, we know that A sub Tm complement is reducible to A sub Tm, but A sub Tm complement is not mapping reducible to A sub Tm. Okay, so here's another thing, an explanation. So for any undecidable and Turing recognizable language A, we have A is Turing reducible to the complement of A, but the complement of A is not, or maybe we can say this, I'll remove that. Okay, so just to make this happen. All right, so we can similarly define a acceptance problem with respect to Oracle Turing machine, A sub OTM instead of A sub TM, which is a set of instances which are encodings of a machine M n comma X, where M is Oracle Turing machine, and M with Oracle A sub Tm accepts X, and this is undecidable relative to A sub Tm. So this is always now with respect to A sub Tm, proved by diagonalization, which is similar to proving that A sub Tm is undecidable. Okay, so this is the notion of Turing reductions. In order to define Turing reductions, we have to look at Oracle Turing machines. Okay, so that's the end of this video.